All right, in problem number 9, we're talking about a sliding ladder problem. So what's going on here? We've got the ground, which of course we're going to assume is level, and then you've got a wall or a house right here that we're going to assume is perpendicular to the ground, and then we have a 5-meter ladder that is, that's not a very good angle. We got a 5-meter ladder, good enough, that's leaning against the house or the wall looking something like this. Now, the first thing I want to talk about here is the lengths of the 3 sides within that triangle. So what's happening here is that the bottom of the ladder is sliding out away from the base of the house or the wall or whatever, and the person who's up on that ladder is now kind of going, things aren't looking so good, and they're probably going to end up falling here. Now, what we want to discuss, though, the 3 sides in that ladder right here, the length of the ladder itself is 5 meters long. That's a constant value right here, guys. That's not changing at all during the course of the problem. We're not talking about an extension ladder that can get longer or shorter. It's just fixed at 5. However, the distances of the 2 legs within this triangle, those are variable quantities. So as I'm reading my directions now, they want to go ahead and tell you that the variable h is the height of the ladder's top at time t. So this distance right here on the left is going to be h. And then they're telling us that x is going to be the distance from the wall right here to the ladder's bottom. So this piece is x. And as I kind of started to put arrows right here, what's happening? X is actually growing as the bottom of the ladder slides out, and h, on the other hand, is actually shrinking. The top of that ladder is falling down and getting closer to the ground here. So that's kind of the setup with where we're at right now. Okay, so in number 9, they say, assume that the bottom slides away from the wall at a rate of 0.8 meters per second. Well, what we're talking about right then is the rate of change of x. So that right there is the derivative, or the rate of change that they told us in this problem right here. The derivative of x taken with respect to t is equal to, what do we got right here? Find the velocity of the top of the ladder. I'm sorry. Bottom slides away at 0.8. All right, so 0.8 meters per second. And again, let's think about this. Since x is actually increasing over time, it makes sense that this derivative here is positive. The derivative that we want to know, let's actually read the question right here. Find the velocity of the top of the ladder at time t equals 2. So they want the rate at which h is changing. dh dt, but specifically they say to find that at the moment when t is equal to 2. Now there's more that comes after that in the problem. If the bottom is 1.5 meters from the wall at t equals 0 seconds. I'm going to put that off until just a little bit later, because what we're dealing with right there are time-specific values. And we don't even want to think about time-specific values until after we've taken our derivative. So let's set this thing up, everybody. What we eventually need is an equation that relates dx dt with dh dt. But before we get that, we need an equation that relates x with h. So we're going to look at this diagram and try to figure out what type of equation ties x and h together. Well, that's going to be the Pythagorean theorem. Legs squared, so x squared, plus the other leg, h squared, is equal to your hypotenuse squared. And since that hypotenuse is fixed or constant, it's always 5 meters long during the entire problem, we can go ahead and put a 5 in there for your hypotenuse and square that to make that a 25. Now again, the only reason that I can put a 5 in for the hypotenuse and not a variable is that that quantity is fixed throughout this entire problem. So there's our equation, and now we're going to go ahead and differentiate this whole thing with respect to t. So we're going to get a 2x times a dx dt there, and then same thing here, plus a 2h and a dh dt, all of which is going to equal, and let's not make an easy mistake right here, the derivative of any constant is going to be 0. Doesn't matter what variable you're differentiating with respect to, the derivative of a constant will always be 0. So here's our derivative equation, and there are 1, 2, 3, 4 variable quantities in this equation. Now, we're trying to find the value of dh dt. That's the one we don't know. We better then be able to put in values for everything else in this problem. So let's start filling in, and right away we run into the hard spot right here. We're going to multiply 2, and what we need now is the value of x, the length of this piece, the distance from the base of the ladder to the base of the wall at the moment in question. Okay, so what are we looking at right there? Now I've got to go back to what I ignored before. What we said is that the bottom of the ladder was 1.5 meters away from the wall at the time when t equals 0. So what I'd kind of write here, guys, is that x of 0 at 0 seconds here is 1.5. And it's growing right here, guys, at a rate of 0.8 meters per second. So we want to know what is x at this moment here when t is equal to 2. So x of 2 is going to begin with this initial value here of 1.5. And then we're going to add to that the distance that it traveled. Well, distance is rate times time. At 2 seconds, moving at 0.8 meters per second, well, 2 times 0.8 is 1.6. Let's add that to the 1.5. And at 2 seconds, after the ladder has started moving, the base of that ladder is 3.1 meters away from the base of the wall. So that took some work right there just to find what x was. Luckily, the rest of this, I think, is pretty straightforward. dx dt, that was given to us, and that's constant throughout this problem of 0.8 plus 2 times, I kind of lied. H is a little bit tricky here too, guys. We've got to do some work to find that. We need to know how far this top of the ladder is right here from the base of the wall at the moment in question. Well, we did the work already to find that the time-specific value of x was 3.1 meters, and we know that this hypotenuse is still 5. And so I'll just go to the other side right here. We can do Pythagorean theorem then, guys. It would have been h squared plus a 3.1 squared is equal to 5 squared. So, doing some quick math, h would end up being the square root of, that would be a 25 minus and whatever 3.1 squared is. So let me go to my calculator. I think I remember this answer, but let's not make a dumb mistake. So the square root of, it was 5 squared, and then minus, we had that 3.1 squared. I think this was 3.9, if I remember that right, 3.923. Okay, so let's write that down. H is 3.923, and I should be specific, at t equals 2. So at the moment in question. So back to where we were, that h value is 3.923. There you go. Okay, so there's the h, and then dh dt is what we were looking for there. dh dt is what is wanted, and all of that is equal to 0. So now from that spot, this should just be a little bit of algebra here to solve this, and hopefully not all that difficult. So let's see what we've got. I think I'll go ahead and multiply all of this out. The 2 times the 3.1 times the 0.8. Don't think I can do that in my head. So here we go. 2 times 3.1 times 0.8, and that's going to make that left side 4.96. All right, so 4.96, and then plus, I'll go ahead and multiply that ugly decimal, 3.923, by 2. But remember, guys, we're never going to manually type in a rounded decimal. I'm going to hit my up arrow a couple times and then do enter, and we'll multiply that by 2. All right, and now we have a very accurate answer of 7.846. And we'll put a dh dt at the end of all that is equal to 0. Let's bring this positive term over to the other side. So 7.846 dh dt is going to equal a negative 4.96. And now we'll get dh dt by dividing negative 4.96 by that 7.846. Now that negative 4.96 was exact. I can type that in. Negative 4.96 divided by, but now I'll just use my up arrow, or I could have hit last answer, and I think what we have right here is the most accurate possible answer we could come up with of negative 0.632. So let's jot that down. Negative 0.632. Everything here, let's see, was being measured in, it was meters per second, so that's going to be our answer here, meters per second. And a quick conversation real quick, guys, does it make sense that that answer is negative? Well, if the bottom of the ladder is sliding out, we said that means the top of the ladder had to be sliding down. H is actually getting smaller as this thing moves along right here, and so that concept of that answer being negative makes a lot of sense. Okay, that's our answer for number 9.